Okay, so let's jump into the last section here. So today we're going to be talking about Gauss's theorem. Oop, that is not a straight line. Not even close to what I wanted. So this is also in your book is called the divergence theorem. These both work. So what we're going to do is consider some vector field that has component functions p, q, and r. And those all could be functions of x, y, and z. We also have that the divergence of f is partial p partial x plus partial q partial y plus partial r partial z. We've learned that from the time that we spent on the divergence. So, thus, for any region E, the triple integral, it's been a while since we've talked about these, triple integral over the region E of the divergence of f dv. What we could do is, because this is now a sum, and the integral is a linear operator, we can write this as partial p partial x dv plus the triple integral of e partial q partial y dv plus our triple integral over e of partial r partial z dv. Okay. So because this is a volume, the region E also is enclosed by some surface that we'll call S. With an outward pointing normal. That we'll call N. Notice that we'll have a surface area integral. And if you have a surface that doesn't have a boundary, so think of a sphere, right? A sphere is a really good example. A sphere, the surface that encloses the sphere doesn't have a boundary, right? That is a closed surface. So just like the line integral that's closed, you have this circle that kind of is in the middle. So this is a closed surface. just notation wise, of f dot ds. So we're trying to find the flux of f through the closed surface. So if we drop our shorthand, remember the flux was calculated like this. Just how much of f is going through the normal of the surface. Well, why don't we go ahead and break up what f is here. This is the closed surface, S. And then we have P in the I direction plus Q in the J direction plus R in the K direction, dotted with Rn, our normal vector, ds. So just like we did with the volume, since this is a sum, we can do 3 separate integrals where we have Pi dotted with n ds, our surface area integral, with Qj dotted with n ds, and our surface area integral with our k hat dotted with n ds. I kept going back and forth between the vector hat and the hat. The normal is always typically a unit vector here, so it's okay to write n hats. Okay, so we broke it up here, just like we did with the volume. Our goal is to prove that the 3 surface area integrals that we have written here match the 3 volume integrals. So we're only going to focus on one of them just for the proof. So we're going to take a look at this last entry here. So we have our surface area integral of R k hat dot n ds is equal to the triple integral over E of partial R partial Z dV. And this is want to show. And then a similar argument can be made for the other 2 equalities. Okay, so how do we do this? Imagine that the region E can be described as the set of all points where x and y are in some domain D. And we have that Z is bounded by some function of x and y, u1 and u2. So here we have that D is the projection onto the xy plane. So if that's the case, what we can do is write our triple integral over the region E of partial r partial z dv as the double integral over our projection D, and then we'll have our single integral in here partial r partial z dz dA. So this is basically how we constructed the volume integrals in the first place, right? We have some volume, we project it down to some coordinate plane, and we do the direction that we're going in for the projection first, right? So we're projecting to the xy plane, so we have our z integral first, and then we just do some area integral. Okay. So we can actually use the fundamental theorem of calculus on this first integral in here. This is still our double integral over D, but now we have a z derivative of r, and we're integrating with respect to z. So we get r x y u2 of xy minus r x y u1 of xy dA. All right, so we just use the fundamental theorem of calculus here for our z integral. So now what we're going to do is we're going to look at the surface area integral, see if we can match it up with this. So the volume E has 3 different surfaces. So we're going to try to break it up into pieces, right? Based off of our description of E here, we can imagine that it's enclosed by some surface S1 where the normal is pointing up. We can kind of draw a picture too here in a second. We'll have some surface S2 where the normal is pointing down. And let's do a little, because it's not going to be completely vertical. And then S3 where the normal is pointing horizontal. So what kind of thing have we been describing with E? So let's go ahead and just do a quick sketch here. Perhaps we had some surface that defined U1. Maybe it looks something like this. And then we had some surface defined by U2. I don't know why I did dotted lines for those 3 and that solid line for that one. But this, we have some volume here. And you can see that we have some normal that might be pointing in some kind of upward direction here. Then we're going to have some normal that's pointed some downward direction. And then on the sides, we'll have some surface that might be pointing horizontal. And what we'll do is we'll just break up these surfaces into 3 different categories. That it's pointing up, it's pointing down, or it's pointing horizontal. Those are all kind of air quotes on them. So notice that the double integral for S3 of R k hat dot n ds is equal to 0. How do I already know that? Because take a look at what the dot product is representing. I have some scalar function in the z component, right? And then I have some normal dotted with n. Since k dot n is equal to 0. So I don't even really need to worry about the surface area integral for the sides. Thus, the closed surface integral only is going to rely on S1 and S2, basically the top and bottom surfaces. Okay, so the surface S1 is given by C is equal to U2 of X and Y, which means that we can write G as Z minus U2 of X, Y is equal to 0. Right, this is the behavior of our surface, which means that the surface area integral of R k hat dot n ds can be written as the area integral of D of R k hat dot n, the magnitude of the gradient of G, and then the magnitude of the gradient of G dotted with k hat, since we're projecting to the xy plane, dA. So let's simplify this a little bit. But we know that the normal for the surface is plus or minus grad G over the magnitude of grad G. And what we're going to do is we're going to choose the plus or minus that guarantees that the gradient is pointed upward. So we get the area integral over D of R k hat dotted with plus or minus grad G over the magnitude of grad G, magnitude of grad G, and then the magnitude of grad G dotted with our k hat dA. Okay, so notice here that our magnitudes of the gradient of g are going to end up canceling. Then we have that grad g over our the grad g dotted with k. The cool part is we know that the grad g is going to have a z component that's just 1, right? Just go ahead and look at the gradient here. You'll have negative ux or u2x. Actually, why don't we just go ahead and write it at least once, and then we'll replicate it for the other side. We'll get negative u2x, u2y, and then 1, right? If I want this to be pointed up, I'm going to choose the positive version here. And when I take this dot product here, I also get a 1, so this denominator becomes 1. This numerator, because it's being dotted with k, just like this denominator here, is also going to be 1. So we end up with the area integral, where the integrand simplifies to r of x, y, and then remember, for a surface area integral to an area integral, we have to remove the variable that's not present using our constraint function, g. Right? Well, I would have a z here, but I know that z is equal to u2 of x, y, dA. Okay, that looks like a piece of the puzzle. So we can repeat this process. But now we'll do it for surface 2. So we know the surface area integral of r k dotted with n ds. So kind of just look through the argument here. I need now the norm. These are all going to be u1s instead for this surface. And this time I want the normal to be pointing down. So I choose the negative. You still get the magnitude of -1 here. So you still get a 1. These end up canceling, and you're still dotting it with k hat here. So you get negative the area integral over d of r x, y. This time it was characterized by u1. And we have dA. Then the total surface area integral over this closed surface S, rk dotted with n hat, ds is the area integral over d of r x, y, u2 minus r of x, y, u1 dA. Well, that is the, oh no, should be said, I said u1 and I put a 2 there. There we go. So that's the same result that we got from the volume integral. So Gauss's theorem man, I cannot do good lines today, is that the closed surface area integral that calculates the flux through the surface of the vector field F can be rewritten as the volume integral over the enclosed volume of the divergence of f. Pretty cool. So you can think of this as a generalization of greens to a higher dimension. Remember, we saw something very similar with the flux of greens, right? So if you have a flux line integral, you could write this as the divergence of the area integral of the divergence of f. Well, this is again a closed entity. This is now a closed surface, and the flux through that surface is equal to the divergence over this volume integral. How much of the divergence is inside this volume? And if you kind of think about it physically, it makes sense, right? Remember, divergence was this physical meaning of how much is escaping that single point. And if you add up all of the things that escape the volume, it is how much is going through the surface. So physically, it just makes sense too, but we've also proved it mathematically. So, but let's do a physical kind of aspect. We are engineers. So let's do some examples. Let's find the net outward flux of the field they all share a common denominator that is x squared plus y squared plus z squared to the 3/2 power x, y, z. Across the boundary of the region where x squared plus y squared plus z squared is bounded by a squared and b squared. Okay. So let's kind of think about this for a second. What is the region that's being described and this boundary? So if I look at this x squared plus y squared plus z squared kind of reminds me in spherical coordinates. I know we haven't talked about spherical coordinates in a while, but this is rho squared, right? This is the radius squared. And then I have an a squared and a b squared. So to me, this looks like a circle or a sphere of radius a and a sphere of radius b, right? The spherical shells of radius a and b. And then I'm trying to find the net outward flux of this field on the boundary of those surfaces. So let's kind of do a sketch. Let's just do like a cross-sectional view. Can't really draw spheres all too well, especially when we have an inner sphere and an outer sphere. But just a cross-sectional view of kind of what's going on. Is we have some outer sphere with radius b, that's still a vector, and then we have some inner sphere of radius a. So that's what's being described here. These are closed surfaces. So this one here is just a surface of a sphere. We know that to be closed. The one in the interior is also a closed surface. Their normals are always pointed out of the object itself. So that would be the normal for that surface, and that would be the normal for that surface, always pointed out of the volume. So what we could do to find the total outward flux is I could do a flux integral over the sphere in the interior, and then I could do a flux integral of the outer sphere. Oh, that's two different flux calculations I would need to do, right? And we haven't even really talked about doing surface area integrals for spheres, right? We've done something similar for a cylinder where we project to the theta z plane. You could do that in spherical as well. You could project to the theta phi plane for spheres and do surface area that way. Or you could split the sphere in half and then project the top half down to the xy plane and then worry about the bottom half and project that to the xy plane. Could do that as well. But that just makes things a lot more complicated, right? Doing this brute force way using surface area integrals would require some work. But Gauss's theorem gives us an alternative. The area or the volume in between these surfaces is something that we could use for Gauss's theorem. These are both closed surfaces, right? It encloses some volume, right? So what we could do is just look at the volume integral over this region and just look at the divergence of f. So let's go ahead and do that rather than do all these surface area integrals. So the first thing we need to do is calculate the divergence of f. So this is our partials with x and y and z dotted with x squared, y squared plus z squared to the 3/2. Make that 3/2 a little better. 3/2. The vector x, y, z. Okay. Well, let's take a look at the x derivative. The x derivative of x over x squared plus y squared plus z squared to the 3/2 is equal to, we have to do a product rule here. So we take the derivative. So I'm going to think about it as x and 1 over this guy here. Instead of doing a quotient rule, I can do it like a product rule. This is 1 over the original x squared plus y squared plus z squared to the 3/2. And then I keep the x and then I multiply by the derivative of 1 over this denominator. So we get minus, we end up with a 3x squared in the numerator. And then the denominator is x squared plus y squared plus z squared to the 5/2. So you can imagine if I take the y derivative of y over this thing and I take the z derivative of z over this thing, I get very similar forms here. So if I do partial y of y over x squared plus y squared plus z squared to the 3 halves. I get 1 over x squared plus y squared plus z squared to the 3 halves minus 3y squared over x squared plus y squared plus z squared to the 5 halves. And then finally, our z derivative give us a very similar form. This time we just have a 3z squared in that second numerator. Okay, so the divergence of f is the sum of all of these. So I wrote them kind of in columns for us. So we're going to group all of these terms here. So there's 3 of them. So we'll have that this is equal to 3 over x squared plus y squared plus z squared to the 3 halves. Then I have a common factor of 3 for all of these over this denominator, but then I have an x squared plus y squared plus z squared. So this is all minus 3 x squared plus y squared plus z squared over x squared plus y squared plus z squared to the 5 halves. Well, on this second term here, I have an x squared plus y squared plus z squared, right? So that gets rid of one whole factor of this. So we can cancel out the numerator, and then the denominator becomes to the 3 halves power. And then we still have this 3 kicking around. Well, that's exactly this term here. And we have a subtraction. So the divergence of f is 0. Thus, the total flux through our surface F via Gauss is the integral of the divergence of F dv. But the divergence of F is just 0. So a triple integral over 0 is still going to be 0. So that means the total flux going through that surface is 0. All right. Why did this happen? What's going on here? So this translates to the flux on the inner and outer sphere canceling. You will see this result when F represents an electric field or a gravitational field, oh, should use a capital here, this is his name, as Gauss's law. It's a cool thing. And there's a reason that we actually picked this f function, or this f vector field. It is the vector field that is associated with either an electric or gravitational field. And if you think about what that is, so you have some kind of field, perhaps like this. Oh, no. Here we go. F. And it, in fact, turns out that these, this particular vector field is a conservative vector field, which means that I can write it as the gradient of a scalar, where we have a potential field. And that's what you commonly associate with, gravity, right? What is this gravitational potential function, right? And it has a vector field that goes associated with it as well. So the fact that this was a conservative vector field allowed us to get a 0 here. A conservative vector field, remember, meant that the curl was 0. So there wasn't really any like revolution for this vector field. It was all kind of there's no revolution to it. And the way that this thing is pointed is always in, if you can think about it, this is always pointed exactly out of the origin, so it's radially dependent. So however much escapes into the volume will be the same amount that escapes out of the volume. Hence, we get 0. So we've done it math-wise, and we've done it kind of using logic, right? Based off of what our vector field kind of looks like. And if you've taken like a physics 2 class, you'll know this as Gauss's law. Here it is mathematically, why this is the case. Okay, so let's do some other applications. Actually, why don't we take our 5-minute break here? I did go a little bit over. Why don't we take our 5-minute break, and then we'll continue to talk about exciting aspects for Gauss's theorem. Okay, we're back. We talked a little bit over the break. For those of you that weren't here, just to reiterate, it's not necessary that a conservative vector field gives you 0 here. We need that the divergence is equal to 0. But I just wanted to point out that gravitational fields and electric fields are conservative vector fields as well, because that showed up in a prior exam, that knowledge. Okay, so let's do some more applications. Another use of Gauss's theorem is in fluid flow. So we're going to talk a little bit about fluid flow. The hydrodynamic the continuity equation states that the divergence of f plus partial delta partial t is equal to 0, where delta is the density function that inputs 3 spatial coordinates and then a temporal coordinate. V, that's not directly in the equation, but you'll see here in a second, of x, y, and z is the velocity field and F is delta times V. So if you have a velocity and you're multiplying it by this density, you can kind of think of this as a mass per second type of thing. So we state or sorry, not state, we start with the surface area integral of f dot n ds. So this is the flux integral, right? I'm calculating how much of f is going through the surface S, which is the rate at which mass leaves the volume E through S. Here's a question. If continuity is on the exam, will we be given the equation, or is it something we should put on the formula sheet? I think this is too much. This is just an example of where Gauss's theorem is also used, but I wouldn't test on this. This is just to kind of get you in the scope of Gauss's theorem a little bit. And some people have taken fluid flow. So the volume E through S, so how much is kind of leaving the volume E? Now let's have B be the solid sphere centered at a point Q. The average value of the divergence of F over this solid sphere B is the average is 1 over the volume of B multiplied by the volume integral over B of the divergence of F. So basically we're just trying to prove the continuity equation here. And we're starting with acknowledging that if I wanted to calculate the average of the divergence of F over some solid sphere, what we would do is just say, okay, we would add up all of the values of the divergence of F in the sphere and then divide by the volume of that sphere. The average must be achieved somewhere in the sphere. Let's call that point P. So we get that at some point inside the sphere, we get the average of that. So we have some divergence of F. We're finding the average of it, and it has to be achieved somewhere inside that sphere, and we'll just call that point P. Well, based off of Gauss's theorem, this right-hand side can be written as 1 over the volume of B, the surface area over that sphere B of F dot N dA. So what does this surface area mean? Well, this is the flux, right? So this is equal to, in kind of layman's terms, the rate at which mass leaves the volume B across the surface. That's what that, let's just do a straight line. Yeah. So that's what this numerator means. The denominator is still the volume of B. If we take a limit that the radius of B goes to 0, then the point P slowly becomes the center of the sphere. And the right-hand side becomes proportional to how much, oh, I had it right the first time. How much is leaving the sphere at a single point, which we can characterize as a rate of this density. It's how much is leaving, so it becomes a negative. Thus, we have the divergence of F is equal to negative the change in density. So that's how fluid flow proves the continuity equation. So fluid flow kind of has to obey this. And we start with saying, hey, you know, we have some flux, and this kind of means the rate at which mass leaves. So later on, when we look at the average of the divergence of F, we know that it's achieved at some location. We can write this using Gauss's theorem as this surface area integral, but we already said that this is the rate at which mass leaves B across the surface. And if you keep shrinking that sphere that we just kind of made arbitrary, the point that it achieves its average becomes closer and closer to the actual center of the sphere at any arbitrary point Q. And the volume of B goes to 0, and this becomes how much of the density is leaving as a function of time for that specific one point. And that's how they get the continuity equation. This was just a little excursion into an application that some of you might have seen with fluid flow. I won't go into sinks and sources. But what we will do is finish off with an example of Gauss's theorem. We're not going to do continuity equation stuff. Let's evaluate the surface area integral that calculates the flux of F, where F is the vector field x, y, negative y squared over 2, and z. Where S is the union of z is equal to 4 minus 3x squared minus 3y squared where z is bounded between 1 and 4. On the top, we have x squared plus y squared is equal to 1, where z is between 0 and 1 on the side. And then we have, and z is equal to 0 on the bottom. So we have some surface area, and it looks like our surface area is closed. We have some plane that kind of defines this top. We have a cylinder that defines the side. And then That's not. This is actually not a plane. This is a paraboloid. On the top, and then we have a cylinder on the side, and then we've got a plane on the bottom. And instead of doing 3 separate surface area integrals that calculate the flux through each of these, what we're going to do is use Gauss's theorem. So first, let's get an idea of what this looks like. I'm going to do a plot in the RZ plane. So from 0 to 1, I have that R is equal to 1. So it goes up like this. We have Z is equal to 0. So we have this bottom section here. And then we have Z is equal to 4 minus 3R squared, because we can simplify this X squared and Y squared. And it ends up kind of looking like hits up here at 4, and then here at 1. And it's a paraboloid that kind of comes down like that. So then we're looking at this region. And remember, this is revolved around because we're just doing Z versus R. Okay, so rather than do the surface integral on each of these parts separately, especially because we've already seen how difficult it could be to do it on a cylinder, for the closed surface, we can use Gauss's theorem. So the first thing I'm going to do is go ahead and look at the divergence of F, partial X, partial Y, partial Z, dotted with X times Y, negative Y squared over 2, and Z. This will give me, do partial X here, I get a Y. Do a partial Y here, I get minus Y. And then I do a partial Z there, I get plus 1. So this just gives me that the divergence of F is just 1. So using Gauss's theorem, I can say that the surface area integral over this closed surface of F dot ds is equal to the triple integral over the region E of the divergence of F dV or I can do my volume integral in cylindrical coordinates. Let's just kind of write out what our integrand is first. So our integrand from the divergence of F is just 1. This is 1 times R, remember our Jacobian for cylindrical coordinates. And then I'm going to do dz, dr, d theta. So looking up above at our little structure here, we know that z goes from 0 up until this curve. So this goes from 0 to 4 minus 3r squared. And that means that we're projecting down to the r theta plane. And if you think about what happens when you project this down, you just get the circle. So this goes from 0, and the radius of this circle is going to be defined by the outside of this cylinder here, which just happens to be 1. I guess I didn't write that here. Remember, this is defined by x squared plus y squared is equal to 1. So this goes from 0 to 1. And then we go from 0 to 2 pi to make sure that we revolve that object all the way around. We can do this out. 0 to 2 pi, 0 to 1 of 4r minus 3r cubed dr d theta, or 0 to 2 pi, 2r squared minus 3/4 r to the fourth, evaluated at r equals 0, r equals 1, d theta. Zero to 2 pi. 5/4 d theta, or 5 pi over 2. Okay. So that was pretty easy. We didn't have to worry about doing all of this different surface areas. That would have been actually fairly difficult, trying to do all these different surface areas. This one would be the bottom one you could just write as an area integral. This one we would have to use some trickery. We could just split it up or do projection to the z theta plane. Same thing with this one. This would also need some, I think this one you could project to the xy plane, this top portion here. But those are just 3 different surface area integrals rather than the one single volume integral, which was actually really easy to do. So there are a few things that I want to kind of touch on before we end Calc 3 and then kind of move into review. A lot of the theorems that have required closed entities can be augmented. So imagine that I have maybe, let's do it like this, specifically for doing Gauss. Maybe I've got some bowl here, right? And I do not include the bottom, right? I have some surface, right? And I want to find the flux that goes through this bowl. Well, because it's not closed, I can't inherently use Gauss's theorem. But what I could do, so we say that this perhaps is some surface S1. What we could do is imagine that there is a second surface here, and now it becomes closed. And we'll call that whole thing S of F dot ds. And using Gauss's theorem, we can say that we need to calculate the divergence of F over that volume. But the thing is, I created this S2. So if I wanted to find just the flux through S1, it's no longer closed. What I could do is just move that flux over to the right-hand side, minus the flux over S2. Because the flux of both of these together is my closed surface area integral. So perhaps if S2 wasn't really there and you wanted to know just the flux through S1, you could imagine that the surface integral for S2 is much easier to do, and the volume that is enclosed might also be easier to do. So this is kind of a workaround if you don't have a closed surface. You could kind of augment it and then subtract the components that you would necessarily need to add in order to make it closed. This also works for Green's theorem, right? If you have, say, a line, right? Maybe that's a bad line. Maybe you have a line like this, right? And you want to find the flux that goes through this line. What you could do is put in a second line or a second curve maybe. In this case, maybe it's easy to just do a line like that. And now you've made it closed. So you would find the area integral, and then you would subtract the line integral along this straight edge here. You could even do that for Stokes too. So all of the entities that required closed, you could always augment them to make something closed and then subtract those corresponding pieces. That in itself is very powerful. And I think one of the exams prior, in the earlier semesters, kind of stepped the test taker through this process, where they had to find S1, or the flux through S1, and then they had to find the flux through S2, and then they had to find the volume, and then they had to piece it together saying, oh, look, if I had to subtract this from the other side and done this calculation separately, I would have gotten the right answer. Okay, with that, we're officially done with new material for Calc 3. We made it about 8 weeks in. So I can answer some questions for the remainder of class. I can just kind of miscellaneously talk about things. Tomorrow, I can either answer some questions that people have contacted me, or I can try to do a review session. I think I have a slideshow that goes over some questions that are fairly relevant for the exam. So we could go through those. That might be good. But for now, I guess if you guys have any questions, I can answer those. Otherwise, you're free to leave. So I guess a lot of you are leaving, then stay safe until tomorrow, and then we'll do some review.